Good afternoon, everyone. I would like to start by thanking the organizers for the invitation. This is a very nice conference. The main topic is quantum annealing, but my talk will actually have not a whole lot to do with quantum annealing, but rather with the more general theme of the conference, which is quantum simulations. And I would even say for quantum simulations, a bit of a more peculiar topic which has to do with simulations of physics rather than simulations related to computation. So nevertheless, the connection with quantum annealing is quite strong. A lot of the work we do was inspired by work in quantum annealing. As you will see, and in particular, I will talk about tunable couplers, and there are still some interesting intersections between this work and quantum annealing. This is the outline of my talk. I will first discuss in general terms our system, which is a two-level system coupled to one-dimensional waveguide, and I will talk about the strong and ultra-strong coupling regimes. The main part of the talk will be the discussion of our qubit field tunable coupler. I will discuss the design and its experimental demonstration. And in the final part of the talk, I will discuss our ongoing work on exploration of two main research topics, namely emulation of open quantum systems, of the spin boson model in particular, and then test of relativistic quantum information. And then I will mention briefly how some of this work is relevant for quantum annealing. So the system we are interested in is waveguide quantum electrodynamics. So we have an atom coupled to a waveguide, and the only parameter describing the interaction between the atom and the waveguide is this radiative decay rate gamma 1. When this rate is larger than other decay rates due to other environments of this qubit, you reach the so-called strong coupling regime. An important signature of this strong coupling regime is when you look at light transmission through the waveguide at low power, you expect to see a complete extinction at the resonance of the atom. This strong coupling regime was an important milestone in the field of quantum optics for a long time, and it was observed in several implementations, including quantum dots, molecules, and superconducting qubits. The superconducting qubit demonstration is from 15 years ago, and it was done by Astafiev et al. And it uses a flux qubit, very similar to the system that we use in our experiments, with this flux qubit coupled to a microwave transmission line. And they observed this suppression of transmission through the waveguide, which, as I said, is a signature of the strong coupling regime. Next, I will say a bit about the formal description of the model. This system is described by the spin boson model, which consists of a qubit or a two-level system in interaction with bosonic modes. So these are the operators corresponding to these modes. I write this as a sum, but we essentially think of this waveguide as being infinite in size. So these modes have vanishingly small energy level differences between them. And then you have a transverse interaction with this operator sigma x perpendicular to the qubit basis, and this interaction is bilinear. The characteristic of the environment is the spectral density function J of omega, which is described as a sum over the coupling strength squares and corresponding to different mode frequencies. And for this system, the spectral density is ohmic, so it's proportional to omega. And the only parameter of this model is this alpha SB parameter. So we can think about this the spin boson model as being maybe the simplest open quantum system that has fairly rich dynamics. It is known, and it was predicted a long time ago, that when alpha is small enough, you have dynamics which is coherent. So you observe coherent oscillations, but this coherence is damped due to the bosons. When alpha becomes larger than a half and still smaller than 1, you have incoherent dynamics. And finally, at alpha larger than 1, you have localization. It was already realized a long time ago, nearly 20 years ago now, that when you compare implementations of this waveguide QED platform with real atoms and artificial atoms, there are some interesting differences. These are results from a paper by Devoret et al. in 2007, where the normalized coupling strength is compared for Rydberg atoms and superconducting devices. This normalized coupling strength is the coupling strength of a two-level system to resonator. So this is a single mode, not a continuum of modes that we are actually working with. It's a fair measure of the coupling is the coupling strength divided by the atomic frequency omega naught. The first system considered is a Rydberg atom in a microwave cavity, the kind of system that was studied by the group of Serge Harosh. And what is found is that this normalized coupling strength is dependent on the power of the fine structure constant alpha, and this power is 3/2. Alpha is a bit smaller than 1%, so this normalized coupling strength is a relatively small number. When you then look at superconducting circuits, what is interesting firstly is that this normalized coupling strength also depends on the fine structure constant. This is at first probably a bit surprising because if you think about our systems as mesoscopic systems with properties that are determined by circuit elements. So to see that there is also the fine structure constant creeping in is maybe a bit surprising at first. But what is also interesting besides this is the fact that the normalized coupling strength depends on a different power of this fine structure constant, which is 1/2 for this particular configuration, a Cooper pair box in a waveguide, and then minus 1/2 for this other configuration over here. And without going into the details, what this says is that in these mesoscopic systems, the coupling strength can actually be quite a bit larger than in these systems formed with real atoms. Again, we'll turn back to the case of a waveguide in just a bit, but before doing that, let me introduce our qubit. So this is a flux qubit version called the persistent current qubit. It's been around also for a long time. And it's this ring with 3 Josephson junctions. This is a picture of the qubit. The qubit is controlled with an applied magnetic flux phi QB applied to this ring. This graph over here shows the energy level spectrum as a function of the applied flux for typical qubit parameters. And as you can see, these energy level splittings are in the gigahertz range. And importantly for us, around this symmetry point where the applied magnetic flux is half a flux quantum, the lowest 2 levels are well separated from higher levels. So this system has a very large anharmonicity, and this is something that's convenient for us because this circuit is very well approximated by a 2-level system description. In a basis formed by 2 current states circulated clockwise and anti-clockwise, the Hamiltonian is given by this expression over here. And this is very much the same Hamiltonian that was discussed in the talk just before the break, with some differences, of course, with regards to parameters. But a lot of the physics maps out between these qubits and Fluxonian qubits. So, as I said, we are interested in coupling these qubits to waveguides. And what is really a unique feature of these qubits coupled to waveguides is that you can reach the ultra-strong coupling regime. And this is something that was theoretically realized again a while ago. There was this paper in particular from the group of Juanjo Garcia Ripoll in Madrid, where they calculated the coupling strength of a flux qubit coupled to a transmission line in a particular way where you add a junction here to enhance the coupling. And what is predicted is that essentially if you make the size of this matrix element for an operator corresponding to the coupling large enough, you can reach a coupling strength that takes you to the so-called ultra-strong coupling regime. This regime is defined by the condition that the relaxation rate gamma 1 into the waveguide is larger than the qubit transition frequency, which is denoted by delta over here. So in contrast to the strong coupling regime, you don't have to have a radiative decay rate that just exceeds the decoherence rates, other decoherence channel rates for the system, but you have this rate even comparable or even larger than the qubit transition frequency. So now going back to the discussion of these fundamental limits to coupling strength, you can see here that essentially this ratio is now defined by an even more favorable power of the fine structure constant, which is alpha power -1. So the first demonstration of this of reaching the strong coupling regime was done in an experiment led by Paul Fordiaz, who worked with my group and Chris Wilson group in Waterloo to perform this experiment. So this experiment relies on a flux qubit shown here, which is coupled to a transmission line using this tunable coupling loop. So this loop here allows you to tune the coupling strength over some range, which is very interesting to explore this tunability, but this range at the same time is somewhat limited and doesn't allow it to fully decouple the system. Nevertheless, this led to a convincing demonstration of the fact that the qubit indeed has a decay rate that is comparable to the frequency, and these are some images from the experiment showing that you reach this spin boson model alpha coupling strength exceeding 1/2 and even going close to 1. So following this thread of research, we're interested in developing a coupler between the atom and the field that is a switchable coupler. So this is a coupler that we like to have such that the coupling strength can be turned to 0, so you can have full decoupling between the atom and the field, but you can also change the coupling strength and ideally go to very large couplings, maybe close to the USC regime. And this is motivated by several interesting questions, including simulations of open quantum systems and a test of relativistic quantum information. But it also is an opportunity to look at an interesting gadget related to microwave photonics, which is not something that I'm going to talk about a lot in this talk. So when developing this coupler, we are inspired by early theoretical proposals, including a paper by Sabine et al. On entanglement harvesting, which is a topic I'll say a bit later. But also in particular this paper by Borja Pero-Padre et al., where they proposed the configuration to realize this tunable coupling between a flux qubit and the waveguide. So we pursued this research, but we decided to use a coupler configuration that is a bit simpler and a bit closer to some work that we were doing at that time, interestingly, in the field of quantum annealing. So we worked for a few years in quantum annealing, and in quantum annealing, there is a very popular approach to couplers based on essentially using sort of a modified version of flux qubit. So this diagram here shows two qubits, 1 and 2, that you would like to couple with a ZZ interaction, and the coupler is essentially another flux qubit. This is shown here as a single junction qubit. It doesn't have to be a single junction qubit. So the idea is that this coupler acts as an element with a susceptibility that is tuned by the magnetic field applied to this loop. And this susceptibility is something that you can change over a pretty significant range. And also, very importantly, you can fully turn to 0. So we borrowed this idea and we looked essentially at what we wanted to realize, namely a tunable coupling between the current in the qubit and the current in the transmission line by designing such an element. So the actual circuit looks as shown here. You have two loops here, and this lower loop can be thought of as being the usual flux qubit loop. So this is the system that you want to couple to the electromagnetic field. This other loop here is the coupler loop. And the way it is configured, it basically is another flux qubit. It's a flux qubit with a large transition frequency. And also, we share these junctions between the loop and the transmission, sorry, between the qubit loop and the transmission line in order to enhance the coupling. So This is a picture of the device used in the experiment. This is the entire chip, and what you can see here is the transmission line that forms our waveguide. So that's part of our system, this large environment. This is probed using microwave measurements. And here in the center, you have the qubit and the coupler. So a zoom in on that region shows the qubit and the coupler loop. There is one element that we did not use in this first experiment, namely a detector, a discrete detector that is used to measure the state of the qubit. And in addition to this, there is a resonator into which the qubit is embedded, which is used to detect the qubit state, as I said, and then also additional control lines for the qubit and the coupler. So this is this line over here and this line, this line over here. So I will not spend a lot of time talking about the experiments, but rather just discuss the main results. So the main probe we use in this experiment is microwave transmission through the waveguide. And as I said earlier, the transmission is expected to have a suppression at the qubit resonance frequency, and this is what we observe here. So this graph shows the amplitude of the coherent microwave scattering and the phase versus frequency, and we see this strong suppression at the transition frequency. So both the amplitude and the phase look as expected. The continuous lines, which you can barely see here, are fits to the data. And in order to realize this very good agreement with the experiments, we had to do an extension of previous theoretical analysis for this system, in particular, take into account the finite population of the qubit, in combination with other sources of decoherence. And I'm not going to go over this. This is more for experts, but essentially we had to extend the derivation in this paper to look at this. So now, moving on to the main results, they are essentially summarized on this slide here. So what is shown here are three metrics. First, the qubit transition frequency. So that's the transitional symmetry point. Then the decay rate, and then the spin boson model. And I'm sorry, this should be an alpha ASB. So this is the spin boson model factor. And these are shown over the same range of tunable magnetic flux applied to the coupler. This rate and the alpha ASB are just proportional to each other. So this graph is essentially nearly the same as this one. So firstly, let's focus on the main outcome of the experiment, which is the tunability of the decay rate, or effectively the coupling strength between the qubit and the waveguide. So this is shown by this graph here in the middle. So as you can see, the coupling strength has this clear dip here, and this is the point where you also expect indeed for the coupling to be zero. Let me emphasize that the continuous lines are not a fit of the data, but rather a plot based on independently determined parameters. So this is not just fitting that data. So this coupling here makes sense. We couldn't measure something closer to zero because essentially it's very hard experimentally. You get basically nearly no signal in that range, but we could show this very significant tunability in this alpha ASB between 10 to the minus, just a bit up over 10 to the minus 5, all the way up to 10 to the minus 2. So the coupling does what we expect. In particular, you can turn off the coupling, which is very important for the type of experiments that I'm going to show next. Unfortunately, we could not quite reach larger coupling strengths, which is something we were hoping for. And also, there is a fairly significant disagreement between the measured coupling strength and the theory prediction, which is something that I think requires further extensions of the models that we are working with. Another important feature is that as you change the coupling strength, the qubit transition frequency changes fairly significantly as well. So in particular, in this region over here, it changes by a factor of 2 or so. This is something that we would not like to have, but we have a way to work around this. Next, I will just say briefly a few things about decoherence. What we realized looking at this experiment is that we need to model decoherence quite extensively. An important effect has to do with the fact that the coupling between the qubit and the waveguide is not just transverse, as in the spin boson model, but there is a longitudinal component as well. And as you'll see in a second, this longitudinal component leads to pretty significant dephasing. We also had to look at the usual source of decoherence for flux qubits, but also at control lines. So our control lines are also a bit more peculiar in that they have to be coupled pretty strongly, and also they need to have large bandwidth. And it's a challenge to realize this combination with flux qubits. So when you look at the phasing rate versus the coupling strength, so this is the qubit dephasing at the symmetry point. So we can extract this from our microwave scattering experiments. We see that these measured points over here agree pretty well with the phasing introduced by the transmission line. And this is something that we should have probably realized earlier. You get significant dephasing because you have a low noise contribution, which is something that we can get rid of with a relatively easy change in the setup. When you look at relaxation, the rate is perhaps a bit larger than what we were expecting, but again, this is not too far from what is predicted by a reasonable quasi-particle density in the qubit. So all in all, we have a pretty good understanding of sources of decoherence that are intrinsic and not those due to the waveguide, and these sources are by far not a dominating effect. So let me now move on and discuss what we would like to do with this coupler. And the first topic that we would like to explore is the dynamics of the spin boson model. So the spin boson model has been around for a long time. We see its manifestations in many contexts, in quantum information, condensed matter physics, chemistry, and so on. But what is interesting about our system is that we have a lot of tunability. So if you take all the energy scales of the model, which are the qubit frequency, the decay rate, the environment temperature, and the coupling tuning time scale. Sorry, I did get this wrong. I meant to say the rate of change of coupling. The inverse of it is another energy scale. We can actually cover a lot of this parameter space. So we can set these parameters in any relationship with each other with some limits for some of these conditions here. So this opens the way to exploration of non-Markovian effects in system dynamics. But also, another interesting question is how the states of the qubit and the environment look like for these strong coupling settings. And in particular, the ability to turn the coupling on and off very fast opens the way to look at these correlations between the state of the qubit and the state of the field. So what is interesting here is that the states of the field, once you turn off the coupling, are propagating microwave states. So in principle, this opens the way to measuring these correlations between the atom and the field. So now, I will just tell you a bit about an experiment that is related to this topic, namely looking at the decoherence of a qubit in a strong interacting setting. This is also an experiment done with a flux qubit, and in fact, this experiment was motivated very strongly by quantum annealing. So this device here is a flux qubit, and we look at the probability of Landau-Zener tunneling as you basically go through the avoided level crossing corresponding to the symmetry point. So in this experiment, we measured the probability of excitation as we go across this avoided level crossing. And we see at short time scales, we see good agreement with the Landau-Zener formula for a range of the tunneling, for a range of values for the tunneling strength in the qubit. But then at longer time scales, we see, of course, decoherence kicking in, but what is interesting is how there is a change in behavior when you go between a setting corresponding to a large gap at the symmetry point and a small gap value at the symmetry point. And basically, these two limits are described by a theory that is Markovian for the first case. And for the second case, where we have low coupling strength, we need to include strong correlation effects between the system and the environment in order to understand these results. So this already allowed us to peek a bit into these effects. Let me emphasize that this experiment is different in the sense that the environment is the usual environment of a flux qubit, which is dominated by sources of flux noise. So what we can do with this other platform is use an environment that is a lot more controlled, and also we can measure the environment directly. And another point to emphasize here is that this experiment does not have tunable coupling to the noise, but rather the coupling strength is tuned effectively by changing the qubit tunneling strength. So next, I would like to tell you a bit about another research direction that we have been exploring with this platform, namely entanglement harvesting. So entanglement harvesting is a very important prediction of the field of relativistic quantum information. This is an area that is relatively new, and it's concerned with how quantum information concepts find a place in combination with relativity. And entanglement harvesting, which is what we are interested in, is this prediction that if you take two qubits, in the context of this field they are called detectors, and you couple them to a one-dimensional quantum field very briefly, you can generate entanglement between the two qubits. So each of the two qubits is prepared in, say, their ground state, and then you turn the coupling on very briefly, and then you turn it off, and you look at the state of the qubits alone at the end. And it is predicted that you find a bit of entanglement after you decouple the qubits from the field. So this will not be very surprising in general. Oops, sorry. So this will not be very surprising in general, but what is really intriguing is that the predictions say that some of this entanglement can even be recovered when these turn-on events for the coupling between the qubits and the field are causally disconnected. And specifically, when we think about this in a time position diagram, we think about those two qubits being placed at different positions on the time axis, and the turning on of the coupling is represented by this event, so this vertical line. So that's the duration during which the coupling is turned on. So when you show the causal propagation lines arising from one coupling event, we see that these are disconnected from this from this other qubit over here. So the theory predicts that we should be able to see a bit of entanglement in this regime. So I should say that a lot of this work is done in close collaboration with the group in Waterloo, the group of Eduardo Martinez, who is one of the leading, who has one of the leading groups in this field, in the theory of relativistic quantum information. So we've been working on this experiment for a while, and there have been some really long phases and a lot of setbacks. This device picture over here is one from it's a few years ago now. So that's the time when we had a first attempt to pursue this experiment. So this is an actual device image, a device that we attempted to do an experiment with. The colors are false color imagings for the device. And just to say briefly what is in here, we have our waveguide. So the waveguide is colored in red. So it is these long meandering lines, which is the quantum field, so the electromagnetic field. Then we have two qubits that are positioned here and here. And if you zoom around those regions, this is exactly the kind of structure that I showed before. So we have each qubit is coupled to the waveguide with a tunable coupler, and we have a detector. Each qubit can also be controlled with fast pulses using this line here and this other line over here. And then we have these squid detectors. These squids are embedded in resonators. So we have such a resonator here, another one over here, and then a transmission line that is used to probe those resonators. So this whole device is designed to be able to implement the really fast control pulses that you need in order to look in particular at the causally disconnected regime. So the propagation time of light between these 2 points is about a nanosecond when you go along the transmission line. So you need to be able to work with pulses that are significantly shorter than this. So yeah, experimentally this is very challenging. It's something that is not done very often in the field of superconducting qubits, where a lot of the control is done with relatively narrow frequency and relatively longer times in terms of pulse time. So we developed this setup that is very carefully designed in order to allow the propagation of such signals, and also the electronics that is required for this. And just to give you an idea, we show here examples of pulses as they reach the place where the qubit is. So these are measured at room temperature. And you see that you can control this at the sub-nanosecond level, barely in this case, but still probably enough in order to be able to access the interesting regions in this experiment. There is a bit of distortion, but again, that's something that we can correct for. Another important parameter is the jittering between these two pulses. It's the first time we do measurements like this, or measure jittering at the level of picoseconds, but this also looks in line with what we would like to do. So, so there were problems with this first device, but we could test some functionality of the chip. In particular, we could see that our flux detectors were working. This shows the tunability of these flux detectors, and I will not say a lot more about this. So again, we had to fix some issues with our fabrication. Now we are getting back into this experiment. But well, those problems were sorted out. We also started to look a bit more into theoretical aspects of this experiment. So it is important to note that these models that predict entanglement harvesting are very simple in the way they are set up. So you basically have two-level systems. They are called Unruh-Dewitt detectors in this field, coupled to a Klein-Gordon field. Our platform, so flux-based quantum waveguide quantum electrodynamics, has one important advantage, namely strong coupling. And strong coupling is really important for the amount of entanglement you can extract in this experiment. However, there are also many non-idealities. And there is a long list of them. This is sort of a compressed version here. So, so the first problem is already making the mapping of the Hamiltonian to this model. And in particular, strong coupling, there are certain residual terms in the qubit field interaction that cannot be neglected. This is a problem that has been known in the field for a very long time. It is also known in quantum optics. It's associated with issues such as neglecting terms that correspond to a vector potential. Another issue is the multi-level structure of the qubit uncoupler, which is something that we are not worried about, but we need to work with very fast pulses, and it's a lot more likely that we excite these other levels. The fact that we work with fast time-dependent fluxes also means that we'll probably need to look at extensions of regular circuit quantization that are applicable in this regime, and this by itself is a relatively new area in the field. And finally, we need to look at issues related to finite atom size and field cutoffs. So I will just talk briefly about one exploration in theory that was completed recently, namely the consideration of the fact that our coupler works in a way where when you change the coupling strength, the qubit transition frequency changes as well. And this shows here a graph of a representative device where, as you can see, the qubit transition frequency changes from 7, 8 gigahertz down to 2 gigahertz over a useful range of the coupling. So that's a very substantial change. So we did these calculations of entanglement that is recovered from the device. And this is this plot here. So what this plot shows is the amount of entanglement as the negativity for the two qubits at the end of those pulses. And the regions that are most interesting are those that are just outside the light cone. So this, what's below this line or above this line, corresponds to these causally disconnected coupling events. And this is already a very small amount in the usual setting, as is shown here. But when you take this change in the coupling, in the qubit transition frequency into account, that amount becomes even smaller. So this is something that we should definitely be addressing, and we developed a design that that does this. So this is actually, I'm showing this image also because it's a very recent picture of a device after we've been dealing with lots of issues. So it's very fresh, and I'm personally very excited about this. But also it's kind of interesting because it's a relatively involved flux qubit device. So again, we have, as you can see, this is also a bit of a blurry picture. It's not something that we tweaked a lot, even just taking this picture. But you can see this is the flux qubit again with a tunable, sorry, no, that's the flux qubit loop, that's the tunable coupler. And this is an additional coupling loop that allows you to tune the qubit frequency as you change the coupling strength. So at the end, I would like to just say something about, well, is this relevant for quantum annealing more than the fact that we build on the work on quantum annealing in the field and by our group? Well, I think one place where this could be interesting is if you look at quantum annealing when you have a mix of qubits and bosonic modes, and this is a figure from a paper several years ago from the group of Juanjo Garcia Ripoll, where they consider the system with 3 qubits coupled to resonators. So it's interesting to think of, well, would having tunable couplers help with such a realization of quantum annealing, where you mediate interactions via photons? Mediating interactions via waveguides is, of course, interesting because it gives you long-range connectivity. But of course, there are so many open questions around how this would work and what you could do with this. So I'll leave you with that and just summarize my talk. So I talked about our demonstration of a switchable coupler between a two-level system and the one-dimensional field. Then I discussed our work in these two directions, namely simulations of the spin boson model and relativistic quantum information. Then I also discussed a bit some of the current work on theory and the experimental implementations. And with this, I would like to thank my group, and let me first highlight the contributions of Noah Jansen. He's the senior graduate student who worked on these experiments for a few years. So he developed this tunable coupler device, and he's working on the INQA experiment. Shidai, who's now a postdoc, he was a graduate student in the group. He's now a postdoc at ETH Zurich. Worked on the experiment and some of the theoretical modeling. Then, as I said, we have a close collaboration with the group of Eduardo Martin Martinez, and in particular, recently we did a lot of work with Adam, who's now actually a postdoc in our group. Finally, let me thank our sponsors. So these experiments were supported in particular by NSERC, and we also received support recently from the Canada First Research Excellence Funding. And then we have infrastructure support from CFI and ORF and CMC. And finally, I also like to acknowledge our sponsors for other experimental directions that are leveraged in some of this work. And let me close with a small ad, if I may. We are very interested in hiring students and postdocs working on not only on this topic, but also on other topics in the group. Just to make this a bit more enticing, this is our building in Waterloo. This is where most of our Institute for Quantum Computing research takes place. And we are fortunate to have an excellent fabrication facility and also quite a lot of activity in superconducting devices. So I'll close with this. And yeah, thank you.
Thank you very much, Adrian, for your talk. Time for questions.
Thanks, very nice talk. I had one question. You commented that for fast fluxes, you have to extend regular circuit quantization. Does this mean that when you go to time dependence, you have to locate the external flux in some specific nodes, or is there something else that should be taken into account?
Thank you. Yeah, it is very much what you described. Yeah. So and there was maybe somewhat surprisingly, this is not something that was recognized up until a few years ago in the field. Although circuit quantization was around for say around 30 years or more, depending on how you count that. But yeah, this is what we are talking about. And it is a complicated setting because our circuit has a lot of flux control channels, so we still haven't figured out a good way of modeling this. We don't even know whether it's absolutely necessary, but we think it may be. So, yeah.
Okay, thanks.
Yeah, thanks for that. I just have a question. It's been a long time since I thought about ultra-strong coupling. So I don't know if you could explain. I mean, usually I have a qubit, so an effective spin coupled to a resonator that can hold a large number of photons. And at some point, there becomes a qubit and a resonator that's quite nonlinear. But then ultra-strong coupling, what actually are the hybridized states of qubit and photons when you reach that limit? How can I picture this? Is there an easy way to picture that?
Well, it is. The states themselves become dressed by the environment. Yeah. So one way to think about this is as having the two qubit basis states that are and the environment having shifted positions around this. So and then this picture also leads to this idea of frequency renormalizations and so on, suppression of tunneling and so on. But the actual details of it are challenging to understand even theoretically. So some of this work in Madrid, for example, looked at the spatial profile of the excitations in the waveguide, and even predicting that is quite challenging. And I think the structure of that of these rest states depends on details of the environment as well, including cutoffs in the environment and so on. So yeah, so it is seen as a strongly correlated problem. So yeah, I think there is a mapping onto the Kondo problem, for example, in certain regimes. So it's yeah.
Okay.
I don't have a real answer. It's more of, well, maybe why we find this interesting at this point. Yeah.
Okay.
Any more questions?
Thanks, Adrian. Thanks, Adrian. So you didn't mention much about the device, this waveguide device, but why do you need a squid-based resonator to read out? Is that special about this experiment? I don't know if you can explain.
Yeah, this is a very good point as well. I would say, well, we know we need to do state tomography of the two qubits after we switch off the coupling to the waveguide, and this almost felt like a risk mitigation strategy using the squid-based readout, in the sense that this is understood a lot better than other types of readout for the flux qubit. And also, while dispersive readout is interesting and we use it in certain settings, we didn't find a very convenient way to do it in this setting here, because we don't have a lot of flexibility with introducing significant capacitive coupling. Whereas we know that with the squid, you can actually even mix up the coupling a bit, so you can get some flux coupling, but you can also get some coupling even at the symmetry point based on asymmetry. So it was more a matter of kind of giving us a good chance to have reasonable readout fidelity. And I have to say, I think in the first step, in the first stage of the experiment, I don't necessarily expect that we'll have state-of-the-art fidelity, and we didn't want to focus on that part. But, yeah.
Thank you.
Thank you.